What if I told you your car has a secret guardian angel, one that works faster than you can blink, making life or death decisions up to 50 times a second? You can't see it, but you've definitely felt it, that subtle tug on the wheel or pulse in the brake pedal when things get a little too slippery. Hey everyone, and welcome back to the channel. Today, we are pulling back the curtain on one of the most brilliant and misunderstood safety systems in your car. Forget just ABS and traction control. We are diving deep into the mastermind that ties it all together, electronic stability control. Stick around because by the end of this video, you'll not only understand how it saved your life last winter without you even knowing, but you'll also know its secret weaknesses, why race cars sometimes turn it off, and how it's quietly paving the way for self-driving cars. This isn't just a tech spec sheet, it's the story of how physics, computer code, and smart engineering combine to catch you when you're about to make a mistake you can't take back. Let's get into it. Ever wondered what keeps your car steady when you swerve on a wet road or take a turn a little too fast? That's electronic stability control at work, a system so effective, experts consider it the most important advancement in car safety since the seatbelt. At its heart, electronic stability control is like a digital guardian angel for your vehicle. It's a computerized system designed to prevent skids, loss of traction, and dangerous rollovers. It constantly watches over your drive, ready to step in when it senses the car starting to slide in a different direction than where you're steering. Now you might have heard it called different things. Car manufacturers love their branded names. Mercedes and Volkswagen call it ESP, or Electronic Stability Program. BMW and Jaguar use DSC, Dynamic Stability Control. Toyota has VSC, Honda uses VSA, GM calls it Stabili Track, and Ford uses Advanced Track. But underneath all those names, it's the same life-saving technology, most often simply called ESC. So how does this invisible guardian actually work? It builds upon two other familiar systems, anti-lock brakes and traction control. But electronic stability control goes further by using a network of smart sensors. Wheel speed sensors monitor how fast each wheel is turning. A steering angle sensor knows where you intend to go. And the true brains of the operation, a yaw rate sensor and a lateral accelerometer, detect if the car is actually starting to spin or slide sideways. Hear what happens in a split second. Imagine you hit an unexpected patch of ice in a curve. The car might begin to fishtail with the rear sliding out, that's oversteer, or the front might plow straight ahead, refusing to turn, that's understeer. The electronic stability control computer compares your intended direction with the car's actual movement. If they don't match, it springs into action faster than you can blink. To correct a slide, it automatically applies the brakes to individual wheels. If the rear is sliding out, it might brake the outer front wheel to bring the car back in line. If the front is plowing, it could brake an inner rear wheel to help rotate the car into the turn. Often, it will also gently reduce engine power to help you regain traction. You'll know it's working by a subtle pulsing in the brake pedal, a slight tug at the steering wheel, and a flashing dashboard light, usually an icon of a car with squiggly lines. The car will feel like it's gently correcting itself, getting you back into your lane. The reason this system is now mandatory worldwide is simple. The numbers speak for themselves. Studies show electronic stability control reduces fatal single-vehicle crashes by nearly half and cuts the risk of fatal rollovers by over 70%. It's estimated to save thousands of lives every year across Europe alone. It works in common but dangerous scenarios, emergency swerves, slippery corners, or gravel-covered roads, and it even forms the technological foundation for newer systems like automatic emergency braking. But it's crucial to remember what electronic stability control is not. It is not a performance enhancer, and it cannot defy the laws of physics. It cannot compensate for bald tires, reckless speed, or poor judgment. Its effectiveness depends on good tires and, most importantly, being switched on. While some cars have an electronic stability control off button for very specific situations, like rocking out of deep snow or for track use, it should always be reactivated for normal driving. This life-saving technology first appeared in 1995, pioneered by Bosch and Mercedes-Benz. By 2011, the United States mandated it for all new passenger vehicles, and by 2014, the European Union, Canada, Australia, and others followed suit. Electronic stability control is a silent, ever-vigilant system. It doesn't make you invincible, but it is an incredibly effective partner in preventing the most violent kinds of crashes by helping you stay on your intended path. It's a testament to how smart engineering can watch over us, making sure we and our loved ones arrive safely at our destination. Now that we understand what electronic stability control is, let's look under the hood, beyond the basics, at the fascinating engineering, the clever ways it adapts to different vehicles, what happens when it has a bad day, and where this technology is headed next. Think of electronic stability control not just as a single component, but as a symphony of sensors and processors working in harmony. At its core is the electronic control unit, a computer that makes life-or-death decisions in less than 10 milliseconds, processing data up to 50 times every second. Early systems had their own dedicated brain, but in modern cars, it's integrated into a central vehicle computer, coordinating with everything from the brakes to the power steering. It relies on a network of specialized sensors. The yaw rate sensor, the true heart of the system, measures the car's rotation, whether it's starting to spin. This has evolved from bulky piezoelectric units to tiny, robust MEMS chips, often packaged with its partner, the lateral accelerometer, which feels sideways g-forces. And there's the steering angle sensor, which has moved from simple potentiometers to contactless magnetic encoders, knowing exactly where you intend to steer, up to 1800 degrees of lock. All this information used to travel on a simple network called a CAN bus. Today, it flows into a domain controller, a master computer that manages stability, traction control, and even automatic emergency braking simultaneously, enabling advanced feats like predictive torque vectoring. This intelligence allows electronic stability control to perform different rescue maneuvers for different crises. When a car understeers, pushing wide in a turn, electronic stability control might brake the inner rear wheel to help pivot the car back into the curve. For oversteer, that dramatic fishtail, it brakes the outer front wheel to catch the swinging tail. In extreme cases, like an impending spin on ice, it will brake wheels asymmetrically and cut engine power completely. For tall SUVs, it has special rollover mitigation, braking outer wheels and even stiffening the suspension. It can even detect a trailer starting to sway and apply calculated braking to quietly bring it back in line without the driver needing to countersteer. And this technology adapts brilliantly to different vehicles. On motorcycles, it's called motorcycle stability control, and it has the extraordinary task of accounting for lean angles up to 50 degrees. For massive commercial trucks, the focus is on roll stability control, often estimating the load's weight and height to prevent deadly tip-overs. In high-performance cars, electronic stability control integrates with limited slip differentials and offers a track mode, allowing experienced drivers more slip before it gently intervenes. And in electric vehicles, the game changes completely. With instant, precise torque control at each motor, systems like Rivian's can even perform a tank turn by spinning wheels in opposite directions. Of course, no system is perfect, and knowing the signs of trouble is key. A flashing electronic stability control light on your dash means it's actively working to save you. A solid, steady light is a warning there's a fault. The most common issue is a failed wheel speed sensor, often due to corrosion or debris. Other headaches include a steering angle sensor that needs recalibration after a battery change, or a faulty yaw sensor tucked under your seat that's been damaged by moisture. In modern networked cars, even a communication error between computers can disable the system, requiring professional diagnostics. This reliance leads to a fascinating debate. Does electronic stability control make us safer drivers, or does it make us complacent? Critics argue it leads to risk compensation, where drivers take more chances because they feel protected, and that we're losing the raw skill of controlling a skid. Studies show there's some truth to this behavioral adaptation, yet the hard data from insurance companies is undeniable. Even with changed habits, electronic stability control still delivers a net reduction in severe crashes of 25 to 30%. Most professional drivers, even on track days, keep a sport mode of electronic stability control engaged on public roads for that critical safety net. So what's next for this guardian angel? The future is predictive and connected. Imagine electronic stability control that uses cameras and radar to see an upcoming sharp curve or navigation data to anticipate a known hazardous intersection. We're moving toward cooperative stability, where cars communicate with each other, warning about slippery patches just over the hill. Artificial intelligence will allow these systems to learn your driving style and road conditions, predicting instability before it even happens. And as we march toward autonomous driving, the principles of electronic stability control will evolve from stability control to full motion control, becoming the fundamental language for how self-driving cars navigate our world safely. For you, the driver, this means a few simple rules. Always match your tires in size and wear, as uneven tread can confuse the system. Be mindful that aftermarket modifications, like lifting a truck or adding wheel spacers, can affect its calculations. A weak car battery can even trigger false fault codes, and while you should trust it, understand its limits. Electronic stability control struggles with bald tires, sheer ice, and extreme crosswinds. This technology is so vital that governments have created strict global tests, like the sign-with-dwell maneuver, where a car must swerve at 50 miles per hour and recover without spinning out to earn its safety rating. Electronic stability control represents a profound shift in automotive philosophy, from merely surviving a crash to preventing it altogether. For the average driver, it's a system to trust and maintain. For the enthusiast, it's a sophisticated partner when your skill meets unexpected conditions. And for the entire industry, it's the essential foundation upon which the future of automated driving is being built. Its true genius lies in its subtlety, performing millions of unseen corrections every day, preventing tragedies before they ever happen. That is the quiet, profound measure of its success. Now let's enter the masterclass. Let's dive into the elegant physics, the secret algorithms, the racing controversies, and the breathtaking future that defines the true genius of electronic stability control. It begins with the beautiful, complex physics of a tire on the edge of adhesion. Electronic stability control is built on fundamental equations of motion. Engineers think in terms of yaw moments and slip angles. In simple terms, it's constantly solving a critical puzzle. It knows the car's rotation, the lateral forces at each tire, and the subtle differences in brake pressure from side to side, all to calculate whether the vehicle's actual path matches the driver's intention. The core challenge is something called the friction circle. Imagine a tire has a fixed amount of total grip, like a budget. It can spend that budget on braking force, on cornering force, or a combination of both. Electronic stability control is the brilliant accountant that manages this budget in real time. It detects when a tire is nearing its limit and can trade braking force for cornering force, preventing all four tires from maxing out their grip at once, which is when a spin happens. To do this, it employs a digital brain of astonishing speed. It creates a mathematical reference model of what the car should be doing based on your steering input and speed. Then, it compares that to what the car is actually doing, measured by its sensors. Any difference is an error, and electronic stability control calculates the precise braking force needed to correct it, using a sophisticated approach often rooted in something called PID control. But here the magic. The system can't directly measure everything, like the exact sideways slip angle of the car. So it uses an ingenious mathematical filter, a Kalman filter, to make an incredibly accurate educated guess, updating its predictions 100 times per second. It's estimating the invisible in real time with an accuracy of less than half a degree. Different manufacturers apply this genius in unique ways. BMW's DSC integrates with the entire chassis, can pre-fill brake lines when you lift off the accelerator, and even lightly dries your brake rotors in the rain. Mercedes ESP looks ahead, using navigation and cameras to adapt to upcoming curves, and has a special crosswind assist that fights against steady gusts. Porsche's PSM is performance-focused, allowing greater slip for experienced drivers in sport mode, while Ferrari's systems, derived from Formula One, manage the engine, transmission, and differential as one holistic unit for ultimate control. Yet even this technology has its kryptonite. Intermittent faults can be a detective's puzzle. If the system activates on a dry, straight road, it might be a faulty lateral accelerometer. If it pulses at low speed, think of a dirty wheel speed sensor. And there are failure modes too fast or too extreme for electronic stability control to catch. The violent jackknife of a tractor-trailer, the snap oversteer of a classic rear-engine sports car, or the complete float of hydroplaning, where with no tire contact, there is simply nothing for the system to work with. This leads us to the great paradox. How can one algorithm work for a lightweight sports car on a dry track and a loaded SUV on an icy mountain pass? The answer is adaptive tuning. Modern electronic stability control constantly adjusts its own sensitivity based on estimated road grip, vehicle load, even tire temperature. It might sense load through air suspension or by watching how the body moves over bumps, and it estimates road grip by comparing wheel slip to engine torque. This adaptability sparked a fiery debate in motorsport. In the early 2000s, Formula One teams began flirting with electronic stability control, but by 2008, it was banned, seen as reducing driver skill and creating artificial racing. Yet, in other series like the World Rally Championship or Formula E, it's embraced for safety and to enable closer competition. For track days, dedicated motorsport systems offer selectable maps, letting drivers choose how much slip angle is allowed before the guardian angel steps in. All this happens in a realm where failure is not an option. Electronic stability control is certified to the highest automotive safety level, meaning the probability of a dangerous failure is astronomically low, less than 1 in 100 million per hour. Systems like Bosch's ESP Premium achieve this with incredible redundancy. Dual processors that check each other, multiple independent sensors from different suppliers, and a fail-operational design where a backup system takes over if the primary one falters. This necessity for reliability now collides with new threats: cybersecurity. Imagine the danger if someone could spoof sensor data or maliciously take over brake pressure. Defenses include secure cryptographic boot-up, authenticated messages on the car's network, and intrusion detection systems constantly monitoring for anomalies. As we look ahead, electronic stability control is converging with the most exciting emerging technologies. In brake-by-wire and steer-by-wire systems, electronic stability control becomes the primary controller, not just an assistant. In electric vehicles like the Tesla Plaid, it morphs into torque vectoring too, with instant, independent control of each wheel's motor. High-end performance cars like the Porsche 911 Turbo S even link electronic stability control to the active aerodynamics, adjusting the rear wing angle for more downforce during a slide. And this technology is changing us, the drivers. Studies show that with electronic stability control, novice drivers become faster and more confident, while experts might initially feel it fights their inputs. Insurance data reveals a fascinating truth. Drivers with electronic stability control do tend to drive a bit faster and brake a bit later, a behavioral adaptation, but the net effect is still a massive 30% reduction in at-fault accidents. This underscores a new need for driver education that includes feeling electronic stability control activate and understanding its limits. The future frontiers are staggering. We're moving toward predictive stability control, where cars communicate with infrastructure and each other to warn of black ice around the next bend. Artificial intelligence and neural networks will allow systems to learn from millions of miles of driving, handling edge cases no engineer explicitly programmed. We might see personalized electronic stability control that adapts to your stress level, and quantum sensors 1,000 times more accurate than today's, detecting a slip before it even begins. The end goal is a grand, unified theory of vehicle control. Electronic stability control will evolve from a separate system into the central nervous system of vehicle dynamics, a single domain controller orchestrating steering, suspension, powertrain, and brakes in perfect harmony for optimal stability, comfort, and efficiency. In the end, electronic stability control represents the perfect marriage of physics, engineering, computer science, and an understanding of human nature. It aims to be invisible in normal driving, instantly decisive in an emergency, adaptable to any condition, and more reliable than human reflex. As we march toward autonomy, today's electronic stability control is the foundational layer. It's level 0.5 automation, already correcting our mistakes in real time. The final beautiful truth is this: electronic stability control doesn't just make cars safer, it makes drivers safer. It compensates for our most common, deadly mistakes. It is the technological embodiment of the racing instructor's timeless advice. Look where you want to go, and the car will follow. Electronic stability control is the genius that ensures the car actually does. So let's bring it home. Think of ESC not as a robot taking over, but as the world's fastest and most focused co-pilot. It's there for that one job: to translate your panic into physics and your steering input back into a safe path forward. The crazy part, it does this millions of times a day around the world, preventing crashes that never show up in the news and saving thousands of lives every single year. Here's your takeaway: trust it, maintain it, but never, ever test its limits on a public road. It's a system designed for emergencies, not for entertainment. And if you learn something new today, maybe about that ESC off button you've never touched, or why matching your tires matters, then do us a huge favor. Smash that like button, it really helps the channel. Subscribe if you haven't already for more deep dives into the tech that moves us. And let us know in the comments below, have you ever felt your ESC kick in? What was the situation? Thanks for watching, drive safe, and remember, the smartest safety feature is still the one behind the wheel. See you in the next one.